Welcome everyone. Thank you so much for braving a cold and wet Berlin night on a Sunday. Just a quick logistics thing, there are more chairs stacked against the wall over there, so if anyone wants a seat at the back, please feel free to grab those. My name is Steve Williams, performing as drusnoise. This is Professor Anja Metelmann, and we're here. Thank you. It's always good when the physicists get more applause than the artists. So a quick background on this event. The idea we had together was really thinking about how do we think about bringing sounds that are inspired by quantum physics. So this is not meant to be a direct translation of one physics concept equals one sound, one data point equals one sound, but how do we actually enable creative collaborations between artists and scientists? So we have 3 performances, 3 collaborations that are really quite different. To start, myself and Anja will do a performance with this beautiful old school chalkboard here, about as analog as you can get. And then we'll have a performance by Thomas Deschai, Lukas Grunhout, Bhumika Bhatt, and Asan Georgiev. And I apologize for mispronouncing those names. I probably mispronounced every one there. And then we'll have a short break as well with a performance by Jeanette Petrick, Ian Pop, Mathieu Fachon, and Nicholas Gosling. So there'll be a quick break in between those performances so we can rearrange the stages. But there's a bar, and yes, you know what to do during the breaks. So I'm going to hand it over to Anja, who will talk a little bit more about the science of the night.
Yeah, hello, welcome everybody. I'm Anja Metelmann. I'm a professor at the Karlsruhe Institute of Technology and the University of Strasbourg. I'm a theoretical physicist working on quantum stuff. When we're trying to use quantumness for new applications, new technologies, as you probably have heard, quantum computation is something which perhaps will happen in the future. And I'm joined here with some colleagues, and we are all part of a European consortium, the TruePar consortium, developing new amplifiers. We will hear more about that in the lecture. And this is also how we're going to start with the first act. So when Steve and I started talking about what we do, we realized that we actually use the same words. We talk about amplifiers, about resonators, about oscillators and filters, using them differently, but in the end, the same words. And then we start thinking about how can we translate that and which language can we use. And language of sound is the language we will use tonight. And we will kick it off with the lecture, a sonic lecture, which is more or less the theory behind what happens after. So I'm the theorist, the other are all experimentalists, so they know how to actually do things. And important is, this is really not meant to be understood. So don't worry. It's really meant to give you an impression about how we do quantum physics. And as I said to my students, I always give them citation of Feynman, but nobody truly understands quantum mechanics, so don't panic. computation purposes, you need two distinct levels for a logical subspace, 0 and 1. So we need a system which has distinct, discrete states. The simplest example of a system with discrete states is the quantum harmonic oscillator. The Hamiltonian for such an object is really simple. It's omega c, which is the frequency of the qubit. C dagger C, where C and C dagger are creation annihilation operators of bosonic mode. And we also have to account for a 1/2. Important is I will set H bar to be 1 throughout this lecture. We can straightforwardly determine the energy spectrum of this quantum harmonic oscillator by taking the expectation value of the Hamiltonian in the Fock basis, which will simply give us omega c n plus 1/2. And n is here an integer running from 0 to infinity. So we have a countable infinite system. We can sketch this energy spectrum, and starting from what we know from classical physics, the potential of a harmonic oscillator, which is just quadratic. For n equals 0, we have what we call the ground state. It's a truly quantum feature and exists not in the classical world. We have then the first excited state, the second excited state, and so on. Important is that the distance between energy levels, delta E, which we can calculate as E n plus 1 minus E n, is equal to omega c. So we have equidistant energy levels. To realize such a quantum harmonic oscillator in the lab, we can use electric circuit made out of superconducting material. So if we bring them to cold temperatures, they are dissipationless in principle. The circuit realizing a quantum harmonic oscillator is as follows. We have a capacitor, C, and an inductor, L. And the frequency of this oscillator is simply given by the 1 over the square root of L and C. Such a quantum harmonic oscillator can be controlled with microwave radiation. To address two distinct states. So it makes the quantum harmonic oscillator unpractical to be realized a qubit. So what we need is a nonlinearity. And in superconducting circuits, we have such a nonlinearity called the Josephson junction. Simply material of superconducting two layers intersected by an isolator, which gives us a nonlinear inductance in the form of a cosine potential. If this nonlinearity is not too strong, we can write down the Hamiltonian. We have an harmonic part, which we already know, plus or minus, in this case, the nonlinearity. And if we now look at the energy of the system, we will have the harmonic part minus k, the nonlinearity constant, n squared. So if we draw this now, we have a spectrum which has again a ground state, 0, the first excited state. The distance to the second excited state is distinct from the distance here. So we can use just this subspace as our qubit. So we will use for our qubit the 0 and the 1 state, and we label this as the ground and excited states. If we now are faced with a two-dimensional system, we can change our description and use a two-dimensional Hilbert space. So our Hamiltonian has now the form omega q, the frequency, transition frequency between our two levels. And then we use the Pauli spin operators, which are defined as 1, 0, 0, minus 1. So I use the notation, the excited state minus the ground state. Other operators which we need for today are sigma minus, which is just the transition from the excited state to the ground state, and sigma plus, which brings us from the ground state to the excited state. So it's just the transition between the two states. The general state of a qubit is a superposition of these states. We have alpha, which is a complex number, times the ground state plus beta times the excited state. We have to ensure normalization of our state. So the absolute value, alpha squared plus beta squared, has to be 1. This is a superposition. And we can use the Bloch sphere to represent the state we have. This is a sphere where the north pole is our excited state, the south pole our ground state, and any point is representing a state of our qubit. As every quantum system, the qubit is coupled to the environment and therewith to noise sources. To understand and model the influence of the environment, we will use a quantum master equation. So the evolution of the state of the qubit, rho, has a part which is coherent, but we now have to account for the influence of the environment. We have here the dissipation rate, the energy relaxation rate gamma, and definition here is as usual. We have L of O acting on rho, which has a part which is a jump term, and we have continuous evolution, O dagger O, rho minus 1/2, rho, O dagger, O dagger, O. O is here general operator. Besides having dissipation, we also have dephasing. Of the state of our qubit. These processes are detrimental for the lifetime of a state of a qubit. And to characterize the quality of a qubit, we use time scales, which is T1, which is the energy relaxation time, telling us how the state relaxes to the ground state, which is just 1/gamma. And then we have T2 as the time of how fast the coherent superposition is vanishing. Typical times we have in superconducting circuits is 50 to 120 microseconds. So we want to ensure that our qubit is as isolated as possible from the environment, but we still have to address it. We have to touch it, because we want to know in which state the qubit is. So to realize a controlled measurement, we will couple our qubit to a resonator. So we have our qubit coupled to a harmonic oscillator. So we have a qubit frequency omega q and omega c for this resonator. The resonator is coupled to the outside world via transmission line, and the coupling strength is coupled. Here we already see one issue. With this transmission line, the qubit has another way of losing excitation, which is called Purcell decay. To circumvent this, one implements a Purcell filter, which suppresses the density of states at the qubit frequency. Hamiltonian for such a system is simply having the free energy of our harmonic oscillator. I'm removing the vacuum, we don't need it. We have the free energy of our qubit, and we have a coupling between them, which is called the Jaynes-Cummings coupling. We have sigma minus C dagger plus sigma plus C. So this is an interaction which is just a swapping of excitation between the qubit and our resonator. Are the same, they are in a maximally entangled state, which is a state or a setting which is not optimal for readout. So we want to be in the so-called dispersive regime, where the tuning delta, which is just the difference between the qubit frequency and the resonator frequency, is much larger than G. In this situation, we can perform a Schrieffer-Wolff transformation and get the Hamiltonian in a dispersive regime. It's omega C plus chi times sigma z C dagger C plus the free energy of the qubit. What we see here right away is that sigma z is commuting with this Hamiltonian. This is what we call a quantum non-demolition observable. So this is a QND situation, and we call this measurement a QND measurement, because the measurement will not lead to any additional back action in terms of relaxation of the qubit, but it will experience the dephasing which is required. If we take a look at this Hamiltonian, we realize that the cavity will experience a frequency shift. So if the qubit is in a ground state, sigma z will be -1, meaning that our cavity frequency will be omega c minus chi. If the qubit is in the excited state, sigma z is going to be +1, so our frequency will be omega c plus chi. So the cavity will experience a frequency shift depending on the state of the qubit. To start with the details of the measurement, what we have to add here is a drive. So our full Hamiltonian will contain the dispersive Hamiltonian plus a drive on the cavity. Epsilon of t is a complex quantity. And then we have the usual expression of e to the I omega drive t plus the Hermitian conjugate. Where C and C dagger are creation annihilation operators. What will happen is that the cavity will be displaced in a coherent state, and this displacement will depend on the state of the qubit. Where C and C dagger are creation. If we start out in vacuum, with the cavity. We will either go into the alpha G state, which is happening when the qubit is in the ground state, or we will go into the alpha E state, which happens if we are in the excited state operators. We can represent the state of the cavity in phase space, and we consider the steady state. So we start in vacuum, and we are displaced in the alpha H state or the alpha G state. So we have here the expectation value of the quadrature XE and here XG. If we are on resonant with the cavity, the P quadrature will not have any information on the qubit, only the X quadrature. Important is that this distance between these two states, which as we do a homodyne detection are now the pointer states for our qubit, is maximized. And this happens maximally for 2 epsilon over kappa.
Detecting qubits.
How to build and read out a qubit.
Detecting qubits.
How to build and read out a qubit.
Detecting qubits.
How to build and read out a qubit.
Detecting qubits.
How to build and read out a qubit.
Detecting qubits.
How to build and read out a qubit.
Detecting qubits. Detecting qubits.
There are more components in a measurement of a qubit. We have a microwave source, which is at room temperature, 300 Kelvin, and this will give a signal which is going through some attenuators down to our main system.
Detecting qubits. Detecting qubits.
This goes down in the dilution refrigerator, and we have here a temperature of 20 millikelvin. The signal then leaves and runs through an amplifier, which is at the same temperature stage, through another amplifier, until it's processed on a classical level. Important to know is that the signal leaving the qubit and the cavity contains only a handful of photons. It's a really weak signal. So we need special amplifiers to actually read out this signal. Such amplifiers are called quantum limited amplifiers. And the amplifier output is nothing else as P out equal an input signal, which comes out of our system, plus N add times a gain factor, G. G is a number which is larger, much larger than 1. NAD is the noise added in the amplification process. And a quantum limited amplifier adds as less noise as allowed by quantum mechanics. Meaning that if we amplify both one quadrature, space sensitive, NAD will be actually 0. While for a phase insensitive amplifier, NAD
Detecting qubits.
How to build and read out a qubit.
is 1/2.
Detecting qubits.
How to build and read out a qubit.
So 1/2 of a photon is added.
Detecting qubits.
How to build and read out a qubit.
Quantum limited amplifiers are important.
Detecting qubits.
They have enabled
Read out a qubit.
to detect these signals, perform new measurements, new protocols are fundamental for the research today. One really famous example which was possible because we have quantum limited amplifiers is the single shot readout of a qubit. So if we take a trajectory in time,
How to build and read out
the
a qubit.
probability to be in the excited or the ground state,
How to build
what we
and
will
read out a
observe is going, the qubit is going from the excited state to the ground state.
Detecting qubits.
How to build
And this is what we call quantum jumps.
Detecting qubits.
how to build and read out a qubit.
Detecting qubits.
How to build and read out a qubit.
Detecting qubits.
How to build and read out a qubit.
Detecting qubits.
How to build and read out a qubit.
Detecting qubits.
Thank you. Thank you all so much. Thank you, Professor Metelmann. That was amazing. Thank you. So we're going to take a short break and strip this stuff out of the way and move Thomas's table on stage. So about 10 minutes, we'll come back for our second performance of the evening. Thank you so much.
Definitely never got my full qubit explanation. No,